Hi everybody. Wanted to record in this video today an example of how to balance a redox reaction. These are often introduced in General Chemistry 1 and explored in much more depth in General Chemistry 2. But whichever class you're taking right now, I hope this video is helpful. Basically, when we look at a redox reaction, we're going to be given some amount of starting material. Now, the example I'm going to do today is one in which we are looking at an entire redox reaction. So in this example, we're going to start with the dichromate ion in aqueous solution, and it will be reacting with the oxalate ion, also in aqueous solution, and that will be going to make the chromium-3 ion and carbon dioxide gas. Now, the first step in a reaction like this is to figure out which of the materials is being oxidized and which is being reduced. And so that's a skill in and of itself. What we need to do here is to assign oxidation numbers to each of the elements that's not oxygen. And so what we're doing is to look at the chromium and to look at the carbon in this case. And so when I look at the chromium in the dichromate ion, I see that my oxygens have a charge of -14 altogether, 7 oxygens at -2 apiece. And I have my -2 over here. And so I need something -14 that will equal -2. And so my chromium has an oxidation state of +12 together, or +6 for each chromium. And of course I can see over here that it's +3 for the chromium ion, because it just literally says chromium +3. The same thing we'll do for carbon here. We'll say oxygen from the periodic table is -2 apiece. There's 4 of them here, so that's -8. I have an overall charge of -2, and so I need something. Subtract 8 gives me a -2. That something, of course, is +6, and since there's 2 carbons there, each one of them must be a +3. Now, in carbon dioxide over at the right side, even though this is a molecule and it's held together by covalent bonds, we're still going to use oxygen from the periodic table to give us our reference point, if you want to think about it that way. So the oxygen is -4. I need to figure out what carbon is here to get a total charge of 0, and of course that carbon is +4. So now I've identified the oxidation state of the carbon and the chromium in both instances, in the reactant side and the product side. And what I can see is that the chromium is decreasing its oxidation state from 6 to 3, so that's being reduced. And at the same time, the carbon is increasing its oxidation state from 3 to 4, so that's being oxidized. Some of your problems will just give you a half reaction and ask you to deal with it, or give you some smaller pieces of this. I'm starting with a whole example, all right? Your first step, once you've done your oxidation states, is to separate out into 2 what are called half reactions. And so we'll have here our reduction half reaction that happened to be with the chromium, and we'll have our oxidation half reaction. Each one of those only then includes, the half of the reaction we're dealing with. So now from this point on, we'll write them in pairs. Now, our next step as we go through this is to balance the, what I like to call the main elements, everything except oxygen and hydrogen. And we're going to balance these in the same way that you would do, normally in a chemical reaction. And so I'll add in some coefficients. In my top half reaction, I've got 2 chromiums on the left, and so I need to add a coefficient 2 here to get 2 chromiums on the right. And the same thing is true with carbon. I have 2 carbons on the left, so I need to put in a coefficient 2 on the right to balance those, main group elements, or the non-hydrogen and non-oxygen atoms. All right. Next up, what I'm going to be doing is to balance the oxygen atoms in each case by adding an appropriate number of water molecules. Now remember, redox reactions in general chemistry are occurring in water, so the only things we have available to us are the species we added, essentially here the dichromate and the oxalate, as well as water and its constituents. So we could add in water or hydrogen ion or a hydroxide ion as necessary. Those are in the solution and the solvent, and so they're available for reaction. We're going to be using water to balance our oxygen atoms. And so again, in our top half reaction with the chromium, I see that I have 7 oxygen atoms on the left side, and so I need to add 7 water molecules in order to get those 7 oxygen atoms on the product side. In the lower reaction here, I see I've got dichromate on the left that's got, oxalate on the left that's got 4 oxygen atoms. And I already have 4 oxygen atoms on the right side with those 2 carbon dioxide molecules. So I don't need to go any further. Okay, that part's done. The next step in any redox reaction is to now balance the hydrogen atoms based on, there we go, to add in the hydrogen atoms to offset the water molecules I just added and perhaps any other hydrogens that might be present. I'm going to first add those as H plus ions, okay? And so what I can see here is that I just added 7 water molecules, or a total of 14 hydrogen atoms to the right side of my top equation. So I need to add 14 hydrogen ions to the left side of that top equation to balance. The bottom half reaction has been pretty boring thus far, and it still is. There's no hydrogens there to consider, so we don't worry about it. Once we have our main elements, our oxygens, and our hydrogens balanced, now we're going to have a little bit of a divergence point. So the problem would have told us if we were dealing with this problem in terms of being in an acidic solution or a basic solution. And I didn't tell you right off the top, but this problem that I was looking at told us we were in an acidic solution. So at this point, we'll skip on to balancing the charges. I'll do another example in another video that deals with the basic solution example, in which case we would just add a couple of steps at this point. But carrying on with this particular example, now I want to look at balancing the charges. And so I'm going to go in here and I'm going to try to select a different color for us. What I like to do here is to look at both sides of the reaction and add up the total charge. So for the top half reaction, I've got 14 hydrogens, that's a plus 14 altogether, and I've got a dichromate at -2, so I have a total of plus 12. And I like to add it kind of on the end of the arrow. It's just the notation that kind of I came up doing. On the right side, we'll see that I have 2 chromium-3 ions, and that's it as far as charge goes, so that's a total of plus 6. So I can see I have a charge imbalance, and I need to balance that out by adding some electrons. Remember, electrons are negatively charged, and so I can only bring down the higher of these 2 charges to match the lower one. And I'm going to go ahead and rewrite this whole thing on the bottom, okay? So I'm going to draw a little separating line here, and yes, I still want my orange. All right, so in order to bring that plus 12 charge down to plus 6, I would have had to add 6 electrons over here. And so I have my 6 electrons, the 14 hydrogens that I had from before. All the rest of this is just recopying. All right, 2 chromium-3 ions and 7 waters. So now that top half reaction has balanced main elements, balanced oxygens, balanced hydrogens, and a balanced charge. I'm done with that one for the moment. I'm going to look at my lower half reaction, which had in it that oxalate ion on one side and 2 carbon dioxides on the other side so far. Very boring. Now, if I look at my charges again, yes, still orange, thank you. I have -2 on the left, and I have 0 on the right. So again, I'm adding electrons, so I can only bring the charge down, which means in this case I'll be adding electrons to the right side to bring that charge down, and I'm going to need 2 electrons to do it. At this point, you should have electrons being added to the reactant side for one reaction, the reduction half reaction, and you should have electrons being liberated on the product side for the oxidation half reaction. So if you don't have electrons on one side of one reaction and one side of the other side of the other reaction, you've done something wrong. You need to just start with a new piece of paper. Now each one of these half reactions is balanced, and so if the problem had said, balance each half reaction, we're done. If it's talking like this one about balancing the entire reaction, now we have to think about what's happening in a redox reaction, right? In this case, the oxalate ion is being oxidized. It's releasing some electrons. Those electrons are then doing the reduction of the other species of the dichromate here. So the number of electrons in each half reaction have to match, because I've got literally the electrons coming out of one half reaction and going into the other half reaction. They have to match. And so this number 6 and this number 2, I have to make these match. And what I'm thinking about here is, in mathematics terms, the least common multiple. I'm going to multiply each of these half reactions by whatever factor I need to make those numbers match. And in this case, I hope it's obvious to see that I'm going to take that bottom reaction and just multiply it all by 3. Then I'll have 6 electrons in both cases. All right, so a new separator here. My top reaction says 6 electrons plus 14 hydrogens plus that dichromate ion, giving me 2 chromium 3 ions plus 7 waters. And now multiplying by 3 on the bottom, I get 3 oxalate ions, giving me 3 times 2, 6 carbon dioxides and 6 electrons. Now notice that those electrons match. And so my last step is to combine those two equations together, those two half reactions back together. The electrons are going to cancel out because I've got 6 here and 6 here. They'll cancel. I can cancel out anything else that might be redundant. Sometimes you'll end up with water molecules on both sides. Sometimes you'd end up with hydrogens on both sides, perhaps. You can cancel out anything that's redundant from both sides, and then just recopy everything else. So I have 14 hydrogen ions that reacted with my dichromate, and 3 oxalates. Right, so that's everything left on the reactant sides of both half reactions. To give me, and remember, of course, it doesn't matter what order you write these in. So, however you want to write it, doesn't matter. All right, and that is my reaction for the this process in acidic solution. If I went through and checked everything should still balance. I should still have the same charge on both sides, all the same atoms on both sides. And if we were dealing with this in an electrochemistry sense, I would want to know that it was a 6-electron transaction, so to speak, that I had 6 electrons in that previous step. But for the purposes of balancing a redox reaction in an acidic solution, that's it. That's what I need to do. And I will record another video that explains how to do this in a basic solution. So with that, check the description for a link to a worksheet that spells out the rules that I just went through. Good luck, and keep on doing chemistry.